There's been a little bit of confusion about how to use the microemulsion tool in the new version of the MCP, so thought I would walk you all through it. So we're going to click Begin a Cleaning Test, and then Emulsion, then Start a Cleaning Test. If you select this first option, it's going to kick you back to this screen because you can build Pemulon and xanthan emulsions if you just click Start a Cleaning Test, Yes but Modify, and then Add a Gel. So you'll see here's xanthan, and if you click Make an Emulsion, we can make our emulsion right here. So we can build all of those using that feature. If we go to the second option, make a silicone gel emulsion, that's also going to kick you back because those aren't built in the program yet. Our third option, work with microemulsion phase diagrams, is going to open up this screen. And this particular system correlates to this paper here, the mineral spirits-based microemulsions. It's a really good paper that I would recommend reading just to get an idea of what these types of microemulsions are if you're unfamiliar with them. So this is a ternary phase diagram. We read this just like we read a tease chart or a tease plot. Here at the top, where it's 0.1, that corresponds to 10%, and we read down to the opposite corner. So this is 10%, 20%, 30%. And on this axis in green, we have our surfactant or our surfactant plus co-surfactant system. This particular one comes from the manufacturer already dissolved in shell sol D38, so that's why it's 65% DOS and 32% shell salt D38, and then a little bit of isopropanol or 2-propanol, which increases the solubility of that particular surfactant in both water and mineral spirits. But so this is kind of sometimes considered like a pseudo ternary diagram or a pseudo ternary phase diagram because you have multiple components on this axis, but that doesn't really matter. You would just mix up this solution and then add 10 grams of that or 1 gram of it if you're doing a total 10 gram solution. So you don't really have to worry about that too much. Just remember it's your surfactant and co-surfactant. At the bottom, we have our solvent. And so our solvent selection, we read it just like our surfactant selection. So here 0.1 is 10%, and we'll read up to the opposite corner. And so this is 10%, 20%, 30%. And on this axis, we have distilled water, and we're going to read from right to left for this. So this is actually 10%, 20%, 30%. You can see here actually in this little box over here, you actually have the ratio of solvent to the aqueous component to the surfactant. So if we actually come over here to solvent where it says 1.1, that's actually 10%, and we go all the way up here and we follow that until we run into 0.9, which is 90, our distilled water. And so our orange dot sits right where our ratios balance out. So we have our orange dot sitting right where it should be. One difference between the FileMaker Pro version and the runtime version is that this orange dot is not going to move in the runtime versions. However, you can still use this little calculator over here to calculate your solvent, aqueous, and surfactant components, and then you can just locate where it would be on the diagram yourself the way you normally would. Okay, so you can use these microemulsions if you're doing sometimes what's called an inverted microemulsion. I don't really think that's a correct name. Really, this is a water and oil microemulsion because the solvent is the continuous phase. So if I were to make an emulsion using this particular system, generally, when I make a microemulsion, I want to use as little surfactant as possible. So in this one, if I look, the least amount of surfactant I can use coming down here would be this system in blue. And blue dots are going to represent actual microemulsion systems that have been tested and will actually form a microemulsion. So this particular system, if I want to use as little surfactant as possible, I would come here. And this would be, like 6.5 weight percent out of 100 milliliters for the surfactant in this particular surfactant system. So if I have 10% surfactant, I actually have 80% solvent and 10% water. So if I bring my solvent here to 80% and my water to 10%, we'll see that orange dot moves right there. So that's a microemulsion that will form. It'll be nice and thermodynamically stable, and it actually works. And so again, this system is a little different. It is water and oil, but we can go over some more traditional systems in a second. So if you click on this arrow in the top right corner, you see here's another system. This system uses EcoSurf as a surfactant. This one uses Triton. And then here on the last phase diagram, this is also a ternary phase diagram, and we can use this to build our own systems. So we can add surfactants in here, we can add solvents in here, and build our own diagrams. And that's really useful. So one thing we can do is click right here in that green text. If we wanted to use one of those surfactant systems that already exists, we can just click those here. We can also, however, add in just pure surfactants. So if we don't want to use one of those systems, and I usually wouldn't, we can actually click Done, go to the Solutions database, click Solvent Mixture, change, come up, click Surfactant, and for this, I actually just want to use EcoSurf EH6. So I'll click that, and I want to use just 100% of that. Okay, and I can click Done. Done. So if I go back to my diagram and click here, I can see here is EcoSurf EH6. So I can add that right in. And so if I wanted to make a traditional microemulsion system, I can click here down in this solvent selection. If I wanted to do something like xylenes, which is completely non-water miscible, which is important. That's actually how you define these systems. A true microemulsion contains a solvent that is not water miscible. It does not mix with water or dissolve in water in any proportion. So what happens is that the micelle, the surfactant, is filled with the xylene and contained totally inside of it. And what that does is it creates a micelle that is very strained. It's actually so it's filled with the xylene. The nonpolar tails of the surfactant are pointed inwards. The polar head is pointed outwards, since this is going to be an oil and water system, and that solvent is contained totally inside of it. And so these systems have a very small amount of surfactant and solvent, and that's really a big bonus of them. So with this one, if I wanted to use EcoSurf, I would maybe want to use 1%, so 1 gram of it. For my solvent, if I'm using about 1 gram of EcoSurf, I generally want to use about 0.5 grams of solvent, and there are a lot of reasons for that, but I'm not going to go into any of that here. So if I type in 0.5 grams, well, I want my aqueous continuous phase to be such that I actually only end up with 1 gram of surfactant. So I can change that here. So this is a microemulsion system that I could form just with these three components, with EcoSurf, xylenes, and regular distilled water. What's really nice about this is that you could take any aqueous system that you design in the MCP and substitute it in here, because with the molarities that we're working with those really small molar amounts, which is usually 0.05 molarity of our buffers and chelators, that's really not going to make a huge difference. Be aware that for ionic surfactants, that can make a big difference, especially with salt contents. But here with EcoSurf, it's a non-ionic surfactant, so we don't actually have to be concerned with that too much. So you'll notice here that this is a really small amount of solvent, and that's kind of the point. We want to create micelles that are really strained. And microemulsions are interesting in that they don't dissolve things the way a normal solvent or water system would dissolve something. Due to the particular properties of the micelle with the solvent inside of it, we actually have something that's thermodynamically stable, but also has a high amount of energy, but low interfacial tension. It's a really interesting system, and I really encourage anyone to read some of those papers on microemulsions. So that's a traditional microemulsion system. We can make another system though. We can make what's called a swollen micellar solution. So this is quite different from a traditional microemulsion. So what we're going to do is actually pick a solvent that is water soluble to some degree. So I click here and I want to use a solvent and I don't see it here, so what can I do? I can actually just click done and go to my solutions database and click solvent mixture again. And I actually want to use a solvent that's going to be a hydrogen bond acceptor, and I can pick something like MEK, methyl ethyl ketone. And we're going to use that at 100% concentration. Okay, so let's take a quick look actually at MEK. It's an interesting molecule. So we'll walk through this really quick for people who might be a little unfamiliar with the nomenclature. Methyl ethyl ketone. Here is our ketone. Here's our carbonyl group. We have an oxygen double bonded to a carbon, and branching off of that, we have two distinct R groups, or two distinct carbon-based groups coming off of that. So we have our methyl group here. It's a carbon with 3 hydrogens. Then we have a methylene group to the left, and then a methyl group to the left of that. This is the ethyl portion of it. So we have the IUPAC name butan 2-one. So we have 1, 2, 3, 4. That's the but name, and then 2, 1, 2 own ketone. So 1, 2 butanone, and so that's methyl ethyl ketone. And so this oxygen here actually is going to function as a hydrogen bond acceptor in our microemulsion system. And if you wanted to look at the properties, you could just click properties there and learn a lot more about the materials. Okay, so we're back at our phase diagram. So now we can click here and we see methyl ethyl ketone is right there. So for something like this, methyl ethyl ketone, depending on your source, I've seen it fluctuate quite a bit, anywhere from 20% to 27% by weight, solubility, and water. I generally stick around 20% when I build these systems. So if I select 20% here, and I want 1% surfactant content, there we go. There's our microemulsion system. So what's the difference between a swollen micellar solution and a microemulsion? In a swollen micellar solution, the solvent is dispersed in the continuous phase because it's slightly water soluble. So the continuous phase is going to contain some of what's going to be the discontinuous phase, or the dispersed phase, which is the MEK. So it's going to be floating around freely and interacting with the water. What it's also going to do, however, is occupy the center of that micelle, as well as the interface between the micelle and the aqueous continuous phase, or inside what's called the micelle shell. So you actually have solvent migrating in and out of the micelle, making space inside the micelle, doing a lot of interesting things. It provides a lot of interesting properties of the micelle, interesting solvent abilities, and you can use these for a number of different things. What I like to use them for is for the de-wetting of polymer films, and this particular system actually works very well for that, and I have a paper coming out that actually describes this system in depth, so that should be out in September. Okay, to recap, a microemulsion is a system in which we have a non-water miscible solvent contained entirely inside the surfactant micelle, creating a highly strained but thermodynamically stable system. It has a lot of unique energetic properties. A swollen micellar solution, which we'll switch out again here, can contain a much larger solvent content. However, the micelle is still only going to contain about the same amount of solvent as in the microemulsion. But here we have the solvent dispersed in the continuous phase, but it is water soluble. So it is mixing around freely with the water while also migrating in and out of the micelle. So that's really the big difference between the two. So hopefully we can go over these more in the future. Let me know if you have any questions.